Okay, let us start. So, we started with non-unital Banach algebras in the last lecture. Before that, we had proved Gelfand-Neumach theorem for commutative C-star algebras with identity. Now, we will see how Gelfand-Neumach theorem looks like for commutative C-star algebras without identity. So, we will see that we can attach an identity. So, we saw that in the last lecture that for a Banach algebra without identity we can attach an identity and we get a Banach algebra, but it need not be a C-star algebra. So, we will see how to make a non-unital C-star algebra into a unital C-star algebra. Okay. So, we will embed this non-unital C-star algebra as a maximal ideal inside a unital C-star algebra and use whatever theory we have already done for unital C-star algebras and then prove a result for non-unital C-star algebras. So, that is what we will do. Okay. So, let us continue. So, we will start with, so recall that if A is a non-unital Banach algebra, we managed to put this inside a unital Banach algebra, right. So, we defined A tilde to be equal to A cross C. So, this was all A comma alpha, where A belongs to script A, alpha belongs to C, right, with the natural multiplication, right. So, if I take A alpha times let us say B beta, right, then the multiplication is defined by, you think of it as A plus alpha identity and B plus beta identity and then multiply, right. So, you will have A B plus beta A plus alpha B comma alpha beta, right, and the Banach algebra norm. So, this is something you should pay attention to, the Banach algebra norm of A comma alpha, because we are going to change this. Okay. So, this was norm A plus mod alpha. Okay. So, this gave us a Banach algebra and A tilde became Banach algebra with identity, Banach algebra with identity. Okay. But this does not give us C-star algebra norm. So, we saw that for C naught of x, where x is locally compact Hausdorff, we will see how to make a non-unital. So, instead of a Banach algebra we will have a C-star algebra and then we will see how to embed this into a unital C-star algebra. Okay. So, that is the proposition. Let A be a non-unital C-star algebra. So, I am not assuming that it is commutative or non-commutative and all that. The construction works for all C-star algebras, even though we will finally apply it only to commutative ones. Okay. So, non-unital C-star algebra, then there exists a unique norm on A tilde. So, A tilde is something we have already defined, right, that is A cross C, right, unique norm which makes it into a C-star algebra, but the uniqueness part we already know, right, the C-star algebra has unique norm makes A tilde into a C-star algebra. Not just that, so C-star algebra with identity, right. So, it becomes a 0 1 becomes the identity for A tilde. And involution is, so A alpha star would be A star is the involution on script A, right, it is a C-star algebra. So, there is an involution and alpha bar. Okay. So, that is the involution and this norm, the new norm which we have defined on A tilde, which we will define in the proof, agrees with the original norm on A, right. So, this norm agrees with the original norm on A. Okay. So, A is going to sit inside A tilde as a maximal ideal, A tilde will have a norm which makes that into sister algebra with identity, and that norm restricted to A will coincide with the existing norm on A. Okay. So, that is precisely what we want, right. For the Banach algebra this was easy, we could simply define a norm which made it into a Banach algebra, but sister algebra is more non-trivial. So, proof. Okay. So, this is a slightly lengthy proof, not too difficult, but at the same time slightly involved. Okay. So, since A is an ideal in A tilde, right. So, one can act A tilde on A by multiplication, right. A is an ideal. So, you take anything in A tilde and multiply things in A, you will land in A, but A in itself is a Banach space. So, A tilde is acting like linear operators from A to A, bounded linear operators from A to A, right, and you take the operator norm of those elements. Okay. So, essentially you are viewing elements in A tilde as linear operators from the Banach space A to A and look at the operator norm of those elements. So, that will give us a sister algebra norm, right. Operator norm generally should give you a sister algebra norm. First we still have to prove because we are on a Banach space and things like that. Okay. So, A is an ideal, each let us say x alpha in A tilde, right, acts on A by let us say left multiplication. Okay. So, since we are not assuming A to be commutative and so on, we know just better be careful about where we are multiplying by, right. So, acts on A by left multiplication. Okay. Which gives a bounded operator. So, which gives a bounded operator on A. Okay. What does that mean? That is, if I take a point in A tilde, okay, consider the operator, consider the bounded operator. Well, you have to check that it is a bounded operator, but that is trivial from the definition of the norms and so on. Consider the bounded operator tau x alpha. So, this is just a notation I am introducing to make sure that you understand the element x alpha and the operator tau x alpha, which is going from A to A. Okay. What does that operator? Left multiplication. So, tau x alpha, an element in A identified with the corresponding element in A tilde would be A comma 0. Okay. Right. This is simply left multiplication by x alpha. So, that is x alpha times A comma 0, right. So, this, well, we know how the definition is in A tilde. So, this would be x A plus alpha A, right, and 0, right. That is the operator, right. So, if you look at the norm of tau x alpha A comma 0, that is norm of x A plus alpha A, right, because it's viewed as an element in A, right. We are thinking of it as an operator from A to A, even though I am writing it as A comma 0. Okay. So, it is tau x alpha acting on A is x A plus alpha A, and if I take the norm, I know that it is less than to norm x plus mod alpha times norm A. So, it is a bounded operator. Okay. So, that part is trivial. Okay. Now, define a norm on A tilde. So, now I am going to define a norm on A tilde by norm of x alpha to be, you look at this operator tau x alpha and look at the operator norm, right. So, it is an operator from A to A, which is a Banach space. So, that has an operator norm, you take the supremum over the unit ball and things like that. So, this is the norm of the new the element x comma alpha in A tilde, right. So, you take any x comma alpha in A tilde, look at it as an operator from A to A and define the new norm on A tilde by the operator norm of this particular operator. Okay. So, if you want to write it down in words, that is, so the norm x alpha. So, strictly speaking, I should put A tilde here, so that it is clear that it is the norm on A tilde. I will drop the subscripts soon. Okay. It will be clear what norm I am writing. So, this is equal to supremum over norm of x a plus alpha a, but you see these are all in A. So, the norm here is A, okay, with A in A and norm A in script A, right, is less than or equal to 1, right. That is how you write the operator norm, right. So, these subscripts I will drop soon, because whenever I write two elements x comma alpha, then it is the norm in A tilde. If I have only x 0 or x, well, we will prove that this norm reduces to the norm on A restricted to A, and so there will not be any confusion. Okay. So, whatever norm I write, it will be clear. But until we prove that, one should keep in mind that whenever I have x comma alpha or two elements, right, tuple, then the norm is on A tilde, otherwise the norm is on A, right, because these are elements in A. Okay. So, we will drop the subscript, we will drop the subscript subscript A and A tilde. Okay. There will not be any confusion. Okay. So, clearly norm of x alpha, so I will write one more time A tilde, is a semi norm, right, because it is a operator norm of something, and so it will satisfy all those usual inequalities. If I multiply by a scalar, that comes out and all that, right, because it is the operator norm. But we do not know that it is a norm, in the sense that if norm of x alpha is 0, we do not know if x alpha is 0. So, we have to prove that. Okay. So, that is the first step, we prove that it is a norm. Okay. And also it is a semi norm and satisfies. So, this much is trivial and satisfies norm of x alpha into y beta. So, that is the Banach algebra condition, is less than or equal to norm of x comma alpha times norm of y comma beta, because it is the operator norm, right. So, if I have two operators t and s from A to A, then norm of T s is less than or equal to norm T norm s, right. So, the norm of x alpha is the operator norm of tau x alpha. So, this Banach algebra property is automatically satisfied, but we do not know if it is a norm. Okay. So, that is something we will have to check, and then we have to do we have to show that the C star identity is also true, right. So, okay. So, we show that norm x alpha is in fact a norm, okay, norm on A tilde. Okay. So, I have dropped the subscripts of A and A tilde and so on. Okay. Okay. So, suppose x comma alpha is in L tilde, okay, is such that x comma alpha is non-zero, and I am trying to prove that this is a norm. Triangle inequality is satisfied. If I multiply by a scalar, it comes out, because this is defined as the operator norm. We also have the Banach algebra property. What we need to show is, if the norm of x alpha is 0, then x alpha is 0. Okay. So, suppose I take some x alpha which is non-zero and norm of x alpha is 0. So, I need to get a contradiction. Okay. Okay. So, let us try to prove this. So, what does it mean to say that x alpha is 0? So, remember x alpha is acting as an operator on A, right. So, x alpha, so norm of x alpha equal to 0 implies the operator tau x alpha is 0, right. So, how does the operator x alpha act? So, tau x alpha acting on any point, right, a 0 is 0, right. So, but that is simply x a plus alpha a equal to 0 for every a in a, right. So, the norm of x alpha 0 implies that x times a plus alpha a is 0 for every a in a. Okay. From this we need to get a contradiction. Okay. So, keep this in mind because this is going to be used again and again. So, if x is 0, what will happen to that equation? If x is 0, x a is 0 and what I have is alpha a is 0 for every a. So, alpha will be 0. So, this implies alpha is 0. Okay. But we are taking a non-zero element, right. So, x cannot be 0. Okay. So, since x alpha is non-zero, x cannot be 0. Okay. Now, if x is non-zero and x a plus alpha a, so this condition is this true for every a in a, alpha cannot be 0, right, because if alpha is 0, I have x a is 0 for every a, but then a is a C star algebra. So, I can take a to be x star to be there. So, x star is 0 and so norm of that is 0, but that is norm x square, right. So, x will be 0, right. So, let us see. So, alpha also cannot be 0, alpha cannot be 0 because alpha equal to 0 implies x a equal to 0 for every a in a. Okay. So, take a to be equal to x star, we will get norm of x star is 0 implies norm x square is 0 implies x is 0, right, because you are in a and a is a C star algebra, but we know that x cannot be 0. Okay. So, both x and alpha cannot be 0. Okay. So, hence x and alpha both are non-zero. Okay. So, just to make sure that everything is clear, what we did was we started with a element x alpha whose norm is 0, right, that means the corresponding operator is 0. What we have got is a equation like this, which is x a plus alpha a is 0 for every a, and both x and alpha are non-zero elements. Okay. So, we need to get a contradiction. Okay. Okay. So, it follows that. So, it follows that z equal to minus alpha inverse x is a left identity, left right, because we are not assuming a to be commutative, right. So, left identity for a. Okay. Well, why is that? Because we have that x a plus alpha a equal to 0, right. So, so that means alpha a equal to minus x a for every a in script a, right. So, a equal to minus alpha inverse x times a, right. So, minus alpha inverse x, that is my z, is a left identity, right. So, if I multiply it on the left, I get the a back, right. So, that means it is a left identity or left unit. Okay. So, once I have a left unit, then z star will be a right unit, right. So, z star is a right unit, because when I take the star, that is the adjoint, remember we are in A, which is a C star algebra, it will go the other way, and so you get a right identity, is a right identity. Okay. But that implies, so z equal to z times z star, because z star is a right identity, but z is a left identity, so I will get z star, right. So, z equal to z star, and so z is both left and right identity. So, it is the identity. So, hence z is a z is an identity for A, okay, but that is a contradiction. right. We started with a non-unital C star algebra, and if there is an element x comma alpha such that norm of x alpha is 0, norm of x alpha the way we have defined is multiplication action on A, and you look at that operator and say that it is 0, then we are able to construct an identity for A. Okay. So, that is a contradiction, and so it is a norm. Okay. So, hence we get a norm on A tilde. Okay. Okay. So, what is left? So, we need to prove that. So, next to prove that. So, there are 3 more things to prove. One, this norm. So, this new norm, this norm coincides with the original norm on A, right. So, I have defined a norm on A tilde. So, that is a bigger space. If I restrict that norm to A, I want it to be equal to the original norm on A, right. So, to A tilde is a C star algebra. So, it has to be complete, right. It is a, so it is a Banach space. I know that it is a Banach algebra, and it has an involution already, because A has an involution. So, if I take A comma alpha, its involution, its star is going to, the adjoint is going to be A star comma alpha bar, right. So, that we know. And so, once it is complete, I have a Banach star algebra, and I want it to be a C star algebra, right. So, the norm on A tilde should satisfy the C star identity, right. So, what is the C star identity? If I look at x alpha star, x alpha, right, this should be norm of x alpha square, right. That is the C star identity. So, we have to prove all these 3 statements to complete the proof. Okay. All right. So, let us look at the first one. So, what is the first one? The norm coincides with the original norm on A. Okay. So, if x is in A, well, we identify it as x comma 0 in A tilde, right. So, that is same as saying x comma 0 in A tilde. Okay. Tau x comma 0 acting on A comma 0, right. Tau, so tau of any element from A tilde acts on A, right. It is an operator from A to A. So, tau x 0 acting on A 0 is simply x A, right, because there is no alpha there. So, 2 plus alpha is not there. So, it is x A 0, or you can also identify it with x times A. Okay. So, now what am I trying to do? I am trying to prove that the norm on A tilde coincides with norm on A, right. The norm on A tilde is defined to be, you take the element in A tilde, look at the operator and look at the operator norm, right. So, I am taking x 0 in A tilde, which is the element in A, and I want to compute its norm, the operator norm, and say that it is the old norm which I already have on A. Okay. So, norm of tau x 0 A 0, this is equal to norm of x A, right, which is less than or equal to norm x times norm A, right, because everything is now, this norm is happening on A, x A's norm is on A, and we know that this is true, implies, well, so I have A 0 here and the norm of A here. So, this tells me that, remember tau x 0 is not acting on A tilde even. So, I should, strictly speaking, I should write this as A, right, it is acting on A, right, it is a operator from, so tau x 0, just to avoid confusion, is from A to A, right, and the operator norm is there. So, this because the A here and the A on the right hand side tells me that norm of tau x 0, but that is the new norm of x comma 0, right. So, this is what I meant by, I will drop the subscript, the new the x, when I write x 0 the norm is in A tilde, when I write x the norm is in A, right. So, this is actually in A tilde, okay, but I will I will not keep writing the subscript. Okay. This is less than or equal to norm x, right. The norm x this is in the norm in A. Okay. Okay. Now, take, so I need to show that they are actually equal, right. So, take A equal to x star by norm x. So, I can assume x is non-zero, right. So, if x is 0, then you get the 0 operator, the norm is 0, there is nothing to prove. So, take A to be x star x, we get tau x comma 0 acting on A equal to x star divided by norm x, right. So, if I take the norm of this, I will have the norm of this, which is equal to, because everything is happening right hand side, everything is happening in A. So, x star x, right, sorry, x star, what is the norm of x star? That is norm x square. Norm x square, because A script A is a sister algebra, it does not have identity, that is all. So, x star, if I take the norm, I am going to get norm x square, and in the denominator I have norm x. So, I will get norm x, right. So, I know that the norm is less than or equal to norm x, but at some point on the unit ball they are equal, right. So, this implies that the new norm of x comma 0, which is the operator norm of this operator equal to norm x, right, which is in A, right. So, this is in A, this is in A tilde, right. So, the new norm we have defined using the action of elements in A tilde on A and taking the operator norm coincides with the norm on A if the element comes from A, right. So, that is what we have proved. Okay. So, the norm, okay, so that means that is the new norm on A tilde coincides with the existing norm, right, the original norm on A, right, while restricted to A. So, for elements in A it is the same. Okay. Okay. So, hence A contained in A tilde is closed, okay, because the norm coincides and I know that A is complete, right, with respect to the original norm. So, it is going to be closed inside A tilde. If I take any xn in A converging to x, of course, it is Cauchy in A because the norms are same, and so it has to converge to x and x will be in A, right. So, consequently, so it is closed. So, consequently the linear functional. So, I am going to define a linear functional from A tilde to C. Okay. What is the linear functional? X comma alpha going to alpha is continuous. Why is that? Well, if I look at the kernel of this linear, so it is a linear map is trivial, right, because if I take x alpha and y beta, then at the second coordinate I am getting alpha plus beta, right. So, it is a linear map and it is continuous because its kernel is A and kernel is closed, right. So, because the kernel of this map, kernel of this functional equals A, which is closed, right. So, this is something which you have done in the functional analysis course. If I have a linear functional, right, taking values in the complex plane, it is continuous if and only if its kernel is closed, right. Okay. So, it follows that A tilde is complete. Okay. Why is that? Well, roughly speaking, it is A is complete, A tilde by A is one dimensional. So, that is also complete. So, A tilde is complete, okay. But let us write down the argument, okay. So, if x n alpha n in A tilde is Cauchy, is Cauchy in A tilde, right. So, Cauchy in A tilde, then so this implies that x n comma 0 sorry, before that alpha n itself is Cauchy, right. So, implies alpha n is Cauchy in C, right, because x n alpha n is mapped to alpha n by the continuous linear functional, and so if x n alpha n is Cauchy in A tilde, then because it is a continuous linear functional, alpha n is Cauchy in C. Okay. So, this implies 0 comma alpha n is Cauchy in A tilde. Okay. Well, this is something you can check, this is because from the definition we also know that this is equivalent to mod alpha. Okay. So, something is Cauchy with respect to the modulus, then of course, it is going to be Cauchy with respect to that norm. So, once alpha n is Cauchy in C and 0 alpha n is Cauchy in A tilde, from x n alpha n I can subtract 0 alpha n, I will get x n is Cauchy, right. So, x n comma 0 is Cauchy in A tilde, implies, well, the norms on A tilde and A are same. So, x n is Cauchy in A. Okay. So, alpha n Cauchy in C and x n is Cauchy in A. So, there are limits, right, because A is complete, C is complete. So, suppose x n converges to x in A and alpha n converges to alpha in C, then, well, you can check that x n alpha n. So, I will leave this part to you, x n alpha n converges to x comma alpha in A tilde. Okay. So, this is something one has to check, because the norms are defined in a peculiar manner. Okay. So, hence A tilde is complete, hence A tilde is okay. So, next we prove that A tilde is a C star algebra. Okay. So, that is what is left now, but for the time being we will stop. So, if you recall, we started with a non-unital C star algebra, we attached identity to it, and any element in that bigger algebra A tilde acted on A, because A was an ideal, and that gave us a bounded linear operator from A to A, and we use that as the norm. Okay. So, the norm on A tilde, the bigger space, was the operator norm of multiplication by x alpha on the left. Okay. So, that norm we have proved, well, first of all it is a norm, we have proved that when we restrict it to A, we get the original norm on A, and well, it obviously satisfies the Banach algebra property, and we have shown that with respect to the new norm A tilde is complete. So, what is remaining is to prove that it is a C star algebra. So, the norm should satisfy the C star identity. Okay. So, we will stop here and prove that in the next lecture.